So about 2D motion, we're going to consider things moving both in the x and the y directions. Thus, we're going to combine both constant and changing motion, because things moving in the x direction are going to be constant, and things moving in the y direction are going to be changing because of gravity. A ball is dropped from the top of a building. The ball falls 3 times farther during its last second than it did during its third second. If the ball fell 4.9 meters during its first second, how tall is the building, and how much time is the ball in the air?
Because of the way free fall works, if you traveled a distance of x in the first second, that means after that you go up in odd numbers. So basically you'd have 3x, 5x, and so on and so forth. So it said that you traveled 3 times as much as in the last second as in the third second. You have 5x here. Then that means times 3, you'd have traveled 15x in your last second, which happens at 8 seconds. So your total time is 8 seconds. And then to figure out the distance, we know the initial velocity is 0, your acceleration is 9.8 because of gravity, and because you know the time to find the distance, we're going to use this formula. And your initial velocity is 0, so that goes to 0. Distance is going to be equal to 1/2. The acceleration is 9.8 times 8 squared. So we're going to get a distance of 313.6 meters.
During a baseball game, a batter hits a high pop-up. The ball remains in the air for 6 seconds. How high does it rise?
So for this one, if it stays in the air for 6 seconds, that means that it's going to reach its highest height in 3 seconds. So your time is going to be 3 seconds, and the velocity in the vertical direction at this point is going to be 0. So if you said this is your initial velocity, we don't know, but we know the final velocity is 0. So we don't really have an equation relating these, but we can combine 2 equations to figure it out. So in this one, we don't have that initial velocity, so we can solve this equation as initial velocity equals final velocity minus acceleration times time, and plug this in for here. So distance equals velocity final minus acceleration times time plus 1/2 acceleration times time squared. And now we're going to just plug in all our variables. Equals 0. Because acceleration is negative, if we set this up to be a positive direction, so plus 9.8 times 3 plus 1/2 negative 9.8 times 3 squared, and that gives us a distance of 44.1 meters.
Question 3. 2 students are on a balcony 19.6 meters above the street. One student throws a ball vertically downward at 14.7 meters per second. At the same instant, the other student throws a ball vertically upward at the same speed. The second ball misses the balcony on the way down. Calculate the difference in the time the ball spent in the air.
Okay, so first let's get an idea of exactly what's going on. So for a balcony, which is 19.6 meters above the ground, you have ball 1 just throwing straight down at negative 14.7 meters per second because up is positive, right? And then the second ball we're going to throw up at 14.7 and it's going to come down, and at this point here, at equal to the level of the balcony, it's going to have the same velocity of negative 14.7 because equal points have the same velocity, just in opposite directions. And we know the acceleration for both of them is going to be negative 9.8 meters per second because gravity is the only force that we're going to consider. So to figure out the times, we're going to take each individual one. So for ball 1, we know we are trying to figure out time, and we know the distance, initial velocity, and the acceleration. So we're going to plug in our values. So we're going to have negative 19.6, because again, this direction is positive, is going to equal our initial velocity is 14.7 t plus 1/2 negative 9.8 times t squared. So to simplify this a little bit so we can actually solve for it, we're going to divide the entire thing by negative 9.8 so we get nicer numbers. So based off of that, we're going to get negative 2, or we're going to divide by 9.8, is going to give us negative 1.5 t minus 0.5 t squared. And that, if we again divide by another 0.5, we're going to have, and simplify, it's going to be t squared plus 3t minus 4 is going to equal 0. And this is something we can factor, so t plus 4, t minus 1 equals 0. And so then t could either be negative 4 or 1. And obviously you can't have a negative time, so ball 1 is going to take 1 second to fall from here to here. And in ball 2, we have to consider in multiple parts. So the first part we're going to consider is going from here up to here. So here your velocity was 14.7, and here your velocity final was 0 meters per second. So try to figure out the time it took to go from there to there. So to do that, we have the time is equal to the velocity final minus velocity initial divided by the acceleration. So the time is going to give us the velocity final minus initial velocity divided by the acceleration. It's going to give us 1.5 seconds. So that gives us the time it goes from here to here. Then, by the same token, going from here to here is going to take another 1.5. And going from here all the way down to the ground is going to be the same as this because we're dealing with the same velocity. So the time total is going to be 1.5 plus 1.5 plus 1. It's going to give us 4 seconds for ball 2. So the difference in time is going to be 4 seconds minus 1 second. It's going to be 3 seconds difference.
Calculate the velocity of each ball as it strikes the ground.
So both balls are going to have the same final velocity when they strike the ground because they started at the same velocity and traveled the same distance. So we're going to use, considering ball 1 velocity final, it's going to be initial velocity plus acceleration times time. And so it's going to be the negative 14.7 plus negative 9.8 times, we said 1 second for ball 1. So it's going to give us a velocity final of negative 24 meters per second. And that's going to be our final velocity.
Part C. Calculate the distance between the balls 0.8 seconds after they are thrown.
So to find the distance between the two balls, 0.8 seconds. If you think about it, ball 1 is going to be almost toward the ground, and ball 2 is going to be somewhere in this part, because this part takes 1.5 seconds. So let's figure out the position that they're in both times. For ball 1, if we're using this equation here, our distance is going to be velocity times time plus 1/2 at squared. It's going to give us a position negative 14 meters. And then for ball 2, same thing. We're going to use a velocity of positive 14.7, but everything else is going to stay the exact same. And we're going to get a distance of 8.624 meters, and we're going to get the difference between the two, so that's going to give us 23.52 meters.
Question 4. A model rocket is launched straight upward with initial speed of 50 meters per second. It accelerates with a constant upward acceleration of 2 meters per second squared until the engine stops at an altitude of 150 meters. Part A. Calculate the maximum height reached by the rocket.
So for this one, the first thing we need to do is split up the path of the rocket into different segments. The first segment is going to be from the rocket lifts off until when the engine is turned off. So it's going to be segment 1. Segment 2 is going to be from when it's turned off until it reaches its maximum height, because remember, it still is going to have that positive velocity. And segment 3 is going to be once it stops up here and comes back down. So what do we know about segment 1 initially? So segment 1, the initial velocity is 50 meters per second. The acceleration is 2 meters per second squared. The distance it travels is 150 meters. We don't know the final velocity of it at this point, and we don't know the time it takes to get there. Segment 2, we don't know the initial velocity, however, we do know that its initial velocity is going to be the final velocity from segment 1 right here, because that's when it starts going. The acceleration is going to be negative 9.8 meters per second, and the final velocity considered right here is when it stops vertically. It's going to be 0, and we don't know, again, the distance and the time. So the first thing we need to do is figure out the distance, the maximum height. So we have to figure out the distance segment 1, which we do know, plus the distance of segment 2, which we don't know. But to figure out the distance for segment 2, we're going to have to figure out the final velocity that segment 1 stops at. So for this, if I figure out the final velocity is going to be equal to the initial velocity squared plus 2 at the time of the acceleration times the change in distance, square root of that. So it's going to give us square root of 50 squared plus 2 times 150. So the final velocity is going to be 55.678 meters per second. So we can use this here for the initial velocity. So here we know the final velocity is going to be 0 because it stops momentarily, equals the 55.678 squared plus 2 times negative 9.8 as our acceleration, and the distance is what we don't know. And so thus, if we're solving for the distance, we're going to get distance of 158.16 meters. So the total height it traveled, it's going to be this it's going to be the distance of segment 1, which was 150, plus this distance. So 150 plus 58.16. It's going to be a total height of 308.16 5.16 meters.
Part B. When does the rocket reach maximum height?
So the time for it to reach its maximum height is going to be the time it takes for segment 1 plus the time it's going to take for segment 2. So using that, we're going to use this equation. The final velocity is the initial velocity plus acceleration times time, because we know everything else except for the time for both segments. So time is the final velocity minus the initial velocity divided by acceleration. So we're doing this for segment 1. We're going to have the final velocity of 55.678, as we found in the previous part, minus the initial velocity of 50, divided by the acceleration of 2, to give us a time of 2.839. And then for segment 2, we're going to have a final velocity of 0 minus the initial velocity of 55.68 divided by an acceleration of negative 9.8 to give us a time of 5.681. And we add these times together, we're going to get a time of 8.52 seconds.
Part C. Calculate the time the rocket is in the air.
So this is where we have to finally account for segment 3, the time it takes coming down. So we already found the time it takes to reach the maximum height, so for segments 1 and 2. To figure out the time for segment 3. So for segment 3, we know that the distance is going to be the total distance that we found here, the same as the maximum height, right? And then we know the initial velocity is going to be 0. Plus 1/2 acceleration times time squared. We also know the acceleration. So this goes to 0. So we know that the time is going to be 2d over a square rooted. So the time is going to be 2 times 308.16 divided by negative 9.8. Square root that, and this distance is technically negative because we're coming down. So the time we're going to get for this is going to be 7.93 seconds. So that's the time for segment 3, and we're going to add that to the time we found in part B for segment 1 and 2. So plus 0.52, which is going to give a total time of 16.45 seconds.
Question 5. A motorboat heads due east at 16 meters per second across a river that flows due north at 9 meters per second. Part A. Calculate the speed of the boat.
So this part is using basic geometry. If we know that the boat is going 16 meters per second and the current is 9 meters per second, then the velocity is going to go, we're going to use the Pythagorean theorem. So basically the velocity is going to equal the square root of both of the other sides. So the velocity is going to be 18.36 meters per second.
Part B. The river is 136 meters wide. Calculate the time it takes the motorboat to reach the other side.
So this part, we have to only consider the horizontal component, and there's no acceleration, so we're going to just use the distance equals velocity times time, and solving for time is distance over velocity. And so the distance in this direction is 136, because that's how wide it is, and it's going 16 meters per second. So basically the time is going to be 136 divided by 16, which is going to give us 8.5 seconds.
Part C. Calculate the distance downstream the boat is when it reaches the other side of the river.
This part, again, we're going to use some basic kinematics. If we know that the velocity is going up, it's 9 meters per second, and the time, as we established in part B, is going to be 8.5 seconds. The distance equals velocity times time, so your distance is going to be 9 times 8.5, which is going to give us the 76.5 meters.
Question 6. A key falls from a bridge that is 45 meters above the water. The key falls straight down and lands in a model boat traveling at a constant velocity of 3.5 meters per second. Calculate the distance the boat was from the point of impact when the key was released.
Okay, so for this one we have given that you have the key, which is falling, so its acceleration is going to be negative 9.8 meters per second squared. It's going to fall a distance of 45 meters. Its initial velocity is 0 because you're starting off at rest up here, and you don't know the time it takes to actually fall. And then for the boat, you only know that's having a constant velocity of 3.5 meters per second. So in order to figure out the distance of the boat, we have to figure out how much time, because to figure the distance, this one we're going to use the constant velocity equation. So to figure out the time it takes for the key to fall. For that, we're going to use this equation right here. So to figure out the time, we know the initial velocity is 0, so this cancels out. So then the time is going to be 2 times the distance divided by the acceleration square root. So the time is going to be square root of 2 times your distance of 45 divided by your acceleration of 9.8. Again, negative positives cancel out with, it depends on what direction you're going. And that is going to give us a time of 3.03 seconds. So that's the time it takes for the key to fall. So that also will help you determine the distance. The time is going to be the same. So then the distance is going to be the velocity of the 3.5 times the time, 3.03, and it's going to give you a distance of 10.6 meters.
Question 7. Government officials in a faster craft are chasing a spy in a speedboat down a river. Just as the official's boat pulls up to next to the spy's boat, both boats reach at the edge of a 5-meter waterfall. The spy's speed is 15 meters per second, and the official's speed is 26 meters per second. Calculate the distance between the two vessels are apart when they land below the waterfall.
So for this one, we have to consider both the horizontal x and the vertical y components for both the boats. So we know that initially they both only have the horizontal component of the government boat going 26 meters per second and the spy boat going 15 meters per second. But neither of them have an initial vertical velocity. However, we do know that the distance they travel vertically is 5 meters and that the acceleration vertically is 9.8 meters per second. However, we don't know the time, but the time for everything, the entire problem, is going to be the same. So we know that horizontally, we don't have anything causing acceleration, so we're going to use the constant motion equation, and for vertically, we do have acceleration, so we're going to use this. The first thing to figure out is the time, because that's what's going to link the two, horizontal and vertical. So the time, we know the initial velocity is 0 in the vertical direction, so the time is going to be equal to square root of 2 times the distance divided by the acceleration, and then we're going to use this as time and plug it into here to figure out the difference in the distances. So for the government boat, the velocity times time minus the spy boat's time, velocity times time is going to give us the change in difference between the two. The velocity of the government in the x direction times the time, which is 2 times displacement, this is in the y direction, divided by the acceleration, is the velocity, this again is x, the x, remember this is our government, this is our spy. So we're going to plug in our values now, so it's going to be 26 times root of 2, the distance in the y, which is 5, divided by the acceleration 9.8, minus the 15 times the same time again, and that is going to give us a change in difference of 11.11 meters.
Question 8. A ball is projected horizontally from the edge of a table that is 1 meter high and strikes the floor at a point 1.2 meters from the base of the table. Part A. Calculate the initial speed of the ball.
So this one again, we have to consider both the horizontal and the vertical components. So we know that initially when the ball is projected off, it's only going to have a horizontal, it's projected off horizontally, it's only going to have a horizontal velocity, which horizontally has no acceleration, so that's going to be constant motion. And vertically, it's going to have acceleration because of gravity, so that's going to be changing motion. And so we know that horizontally, which is constant, we don't know the velocity that it's bounced off, but we know the distance, it travels a distance of 1.2 meters. Vertically, in the y direction, we know the initial direction in the y direction is 0. The initial acceleration, or the acceleration, is 9.8 meters per second squared, and the distance is 1 meter. So we're trying to find in part A is the initial speed of the ball. So this is going to be the initial speed, basically the speed in the x direction, because that's all we have initially. So for that, we're going to use a constant motion. So the initial velocity x is the distance x over time. Now we don't know time, but time is something that's constant between both the x and y directions. That's what we're going to use to link the two together. So this is the equation we're going to use to solve for time. You know this initial velocity in the y is 0. It's going to go to 0. So their time is going to be 2 times the distance y divided by the acceleration square rooted. So this time then we can plug in for time here. So the velocity in the x is going to be the distance in the x divided by the value we got for time, and now we're going to plug in our values, equals 1.2 divided by 2 times 1, 9.8, so that's going to give us a velocity of 2.66 meters per second.
Part B. How high is the ball above the floor when the horizontal and vertical speeds are equal?
So the horizontal and vertical speeds are going to be equal when the vertical speed equals 2.66 meters per second, because that's what your horizontal speed is constantly going to be. So to connect these, we're going to use this equation right here. And we know the initial velocity is 0, right? And this is we're considering in the y direction. So to figure out the distance that it has traveled. So the distance is going to be the final velocity squared divided by 2 times acceleration. So the distance we're going to get is 0.36 meters. So that is the distance it travels from the top. So the distance from the ground is then it's going to be 1 minus 0.36 meters. It's going to give us 0.64 meters from the ground.
Question 9. A Top Gun pilot practicing radar avoidance maneuvers is flying horizontally at 1,300 kilometers an hour, just 35 meters above the ground level. Suddenly, the plane encounters a terrain that slopes gently upward at 5 degrees, an amount difficult to detect visually. If the pilot doesn't correct his trajectory, calculate the time the pilot has for flying into the ground.
So this one, we bring in a little bit of trig into the problem. So we have the thing flying, and I've kind of enlarged that angle so you have a better idea of what's going on. So we know that it's traveling at this velocity, and it's a constant velocity. Now the thing is, most of our answers, we're going to have to convert this into meters per second, because that's what our other units are in. This is 361.11 meters per second. And so we have two unknowns, the distance and the time. We're going to use a trig to figure out what this distance here is. So we know this angle and this. We know that tangent of 5 is going to be equal to the 35 over this distance. So the distance is 35 over tangent of 5. And so based off that, we know, coming back to this equation right here, the time is what we're trying to solve for is going to be the distance over the velocity. So the distance we established is 35 divided by the tangent of 5 divided by the velocity of 361.11, and so that's going to be the time. So that's going to give us a time of 1.11 seconds.
Question 10. A projectile is fired into the air from the top of a 200-meter cliff above a valley. Its initial velocity is 60 meters per second at 60 degrees above the horizontal. Where does the projectile land?
So this question brings in a lot of different equations and elements. So the first thing you have to realize is the velocity that it's projected off of, the 60 meters per second, has both a x and a y component. So we have to differentiate them because one of them, the y component, is accelerating and the x component is not. So you have a constant and a changing motion. So the y component is the v naught sine theta, and the x component is the v naught cosine theta. So figure out this range. So range, this is you're going to be an x component sort of thing. And so we have to figure out, the thing that connects them is time. So to figure out the time for this entire thing. So this is the time. We have to split this up into different parts. So we're going to split it up right there. So the ascension time and then the descension time. So to figure out the time that it goes to ascend, we're going to use this equation here. So we know that the velocity, the vertical velocity at the top is equal to 0. This final velocity can be 0 in that case. So the initial velocity divided by the acceleration is given the time. So that's going to be time 1 from here to here. Okay, and the second part is going to be figuring out the time for this. The time for this, we're going to have to do, again, multiple things because we don't know the distance from here to here all the way down yet, because we know that this is 200 from here to here, but this part here is something that we don't have to figure out. To do that, we're going to use this equation. We know that the final velocity here, again, is 0. So then the distance is going to be the initial velocity squared divided by 2 times acceleration. And so that's going to be this distance plus, so if we figure that out, again, we're looking in the y direction. So this is going to be the 60 sine theta, sine 60 squared divided by 2 times 9.8. It's going to give us a distance of 137.75 meters. So that's that distance right there. And we're going to add it to this whole distance, add 200 to that, to get a distance of 337.75 meters for this entire thing. Then we're going to use this equation right here to solve, again, from this point, initial velocity is 0, right there. So this cancels out. and you're going to solve for the time for this component right here. So for that component right there, your time is going to be 1/2 d divided by a. Square root is going to be the time. The distance, we're going to use that, so 2 times this distance, 3.75 divided by 9.8. It's going to give us the time, and that time right there is going to be 8.3 seconds. So that's, and then the time here, actually we never figured out, this is going to be the v0 sine 60. This is 60 by 9.8. So that time is going to give us 5.29 seconds. So we add up our two times together. We're getting a total time of 13.59 seconds. So that's the time for the entire thing. So that figures out the whole, so now we have the time, the thing that connects the horizontal and the vertical. So now, finally, we're going to be able to bring in the horizontal components. So that's going to be equation for constant motion. The velocity x we established is v0 cosine theta. And the time we got here at 13.59. So it's going to be our range to figure that out. So equals 60 cosine 60 times 13.59. It's going to be the range of 408 meters.